Hello, thank you for attending my talk. My name is Jonathan, and I'll be presenting our work towards continuous estimation of dissatisfaction spoken dialogue. So as you all know, identifying usability issues in user interfaces is important to improve the experience. And this goes for web pages online, desktop applications, even smart speakers. And how these interfaces are typically improved is you'll have someone making observations as the user interacts with the system. So you have the human watching closely or far, taking the notes as the user interacts with the system. And so the process looks like this. You have the human observer who takes their notes, creating an inventory of quality issues. They can then send that to designers and engineers so that they can fix the issue not only for that one user, but for future users as well. But I think we can do better because this costs money, it's expensive, it costs money, and it costs more people. So what if we'd like to automate this? What would that look like? Well, to automate the process, you would need to record the user's activity and their dissatisfaction automatically as it occurs. Then the interface can be tweaked on the fly using those records. So as an example of something that I've encountered, I've asked an assistant to add something to my shopping list, and she doesn't quite understand it, so I'm repeating it over and over again up until the point where I get a notification on my phone to do it there instead. So because the assistant has realized that I'm not getting what I want, that interface is tweaked so that I can input that some other way. And this works well because you don't need that many people involved. The problem with that is that you need to create the dissatisfaction record automatically. And so how you record the dissatisfaction depends on the interface. But if the system is using your voice, then your dissatisfaction can be measured with your voice. And that's what we do here today. So before I go into how we do this, I'd like to play some clips and give you an opportunity to think how you would detect dissatisfaction. So I'll start with the first clip.
She's currently, like I said, a customer of yours, but we saw that there was an offer for 6 months free if she signed a 2-year contract.
And here's the second clip.
For because I really only have $25 to fix mess, so um,
Which sounds dissatisfied? How did you know? So this is probably easy for humans, but we wanted to know how hard is it to do this automatically? Well, there has been some work related to this, but most of this work has focused on the quality of the entire interaction, whereas you might want finer-grained estimates instead. As an example, if you were a hotel manager and you want to know what part of your system people were having with, maybe it's the part where they arrange the price, or maybe it's the part where they enter their credit card, for example. You want to know what part of that process people had problems with. Another application are call centers. Call centers are a big business, and this kind of quality estimates are used to improve agents' performance. They basically predict undissatisfaction on the customer so that they can give feedback to the agent, something like, your score is a little bit low, maybe you should try to improve your performance this week. So that is exciting work, but we needed funding and we found a sponsor, but our sponsor had a different problem. So in some markets, Google enables users to find merchants by voice search. So they speak what they need and they'll get results as phone numbers. The problem with this is that some merchants don't actually offer what you expect them to. Sometimes they offer it as an excessive price, or maybe they disappoint or trick callers. And this problem is specific, flagging phone calls, but with enough data, it may be applied to more general cases of dissatisfaction. Google provided the funding, but not the data. And also, there wasn't a corpus like this publicly available. So we went out to collect our own. We did this through crowdsourcing so that we can get a wide sampling of customers. So the customers are being played by participants, and the merchants are being played by research confederates. And both of these parties are given instructions. So for two conditions, only half of the calls were set up to satisfy the customer's need. In this example, we have the customer given the instructions to find a place to fix their tire for $10. And so the merchant will sometimes offer the service for $10, and other times they will offer the service for $50, right? They don't give the customer what they need or want, basically. We had a team from the lab and other parts of the university. We ran these studies for a couple months, and we collected 191 calls in total. So in this corpus, the dissatisfaction occurs when the person is trying to do something and expects that it can be easily accomplished, but then finds out that it's not possible. So in that example, they want to fix a tire, but it's going to cost more than they expected, and there's nothing that the merchant can do. For our purposes, an utterance is usually as long as a turn. And so now that we have for each moment or each frame of these utterances labeled for dissatisfaction, we can predict these labels, and we do this using prosody measures. These features measure intensity, pitch height, pitch range, speaking rate, and creakiness. And for context, for each time point, we take multiple measurements over the windows both before and after. Throughout this research, we're only using the customer side audio. These are the types of measurements that we take for each frame. The type of measurement is in yellow and the window is in white. There are 90 measurements in total. Some span longer, farther from time zero, and others are shorter and closer to zero. So as an example, the feature in the very top left is the feature for volume, measuring a window that's about 3.2 seconds ago to 1.6 seconds ago in the past. And so these are our predictors. And now that we have the data and these predictors, we can move on to models. The predictor variables are prosody measures, and the response variable is the level of dissatisfaction. We have two tasks here. The first one is to predict dissatisfaction every 10 milliseconds or for each frame. And the second task is to predict dissatisfaction per utterance or all of those frames. For task one, we predict using a simple linear regression. And for task two, we predict by averaging the frame level predictions. Here's one feature, the volume feature, from 0 to 50 milliseconds into the future. And this histogram was created from the training data. So we took all the frames labeled as neutral and see what their volumes are. And we did the same. We took all the frames labeled as dissatisfied and see what they are. So there is some separation, if you see around 0.4 between neutral and dissatisfied, but it's not much. But it's in combination with all the other features where the separation becomes much clearer. This is a different histogram looking at the output of the regressor, predicting on the dev set. So the regressor is going to output some value between negative 0.2 and 1.6. And since our task is to classify each frame as neutral or dissatisfied, we can set the different thresholds so that the values to the left of the threshold are classified as neutral, and the ones to the right are classified as dissatisfied. The best threshold in that depends on the use case and exactly how the interface is going to be deployed. But we selected the best threshold that fits our problem, which is we want to correctly identify dissatisfied frames as dissatisfied. So we want to focus on detecting dissatisfaction, which is our positive class. And so precision does that. It's measuring what proportion of frames predicted as dissatisfied were actually dissatisfied. Here are the results as precision and recall scores for the different thresholds. The baseline is always going to predict dissatisfied. So starting with the frame level results, when the threshold is 0.6, we have a precision of 70% compared to 36%, and a recall of 28% compared to 100%. Looking at the threshold when it's 0.85, you see that the precision does increase to 95%, but the recall does go down to 3%. And so since the recall is poor, you might want to step it back a little bit. And again, the best threshold depends on the problem. Looking at the utterance level predictions, the single threshold that you see there is the one that we present in our paper. We have a precision of 80% compared to 32%, and a recall of 31% compared to 100%. So in both cases, our models can outperform the baseline when it comes to predicting dissatisfaction correctly. And this is all good, but we'd like to know a little more how it really works. So to understand how each of these features were contributing, we looked at a couple of things. We looked at the histograms for each of the features, like the one that you saw a couple slides ago. We also looked at the coefficients or the weights of the model, and we found a couple things. First is that a neutral frame is more likely to have high volume, low creakiness, and high pitch. Here is an example of that.
My nickname is Al.
Now this might be because we have a tendency to use a pleasant sounding voice. For example, when we say thank you so much. But inversely, we found that dissatisfied frames are more likely to have low volume, high creakiness, and high speaking rate. So here's an example of that.
Tire that is flat because of tire that is flat because of an
Now, for transparency, these are exemplary clips among the few that the model was most accurately able to predict, meaning that there's a lot more room for improvement. To summarize, we succeeded as a proof of concept. We were able to detect dissatisfaction with good results for our sponsor's problem. But we're not ready to replace human observers and engineers yet. There's still a lot more work to come. Starting with what we're working on now, we would like to try different dialogues from different genres and experiencing quality issues of other kinds. So dialogues that experience issues not related to purchasing a product, for example. We also want to evaluate our model in comparison to other models, and this is possible because we made our corpus publicly available. And lastly, we want to investigate language independent detection of dissatisfaction. So we hope that this opens new opportunities for rapid tuning research, even outside of spoken dialogue systems. Thank you for attending my talk, and I hope you have a great rest of your day.